So we're still talking about an ANOVA, which is a one-way analysis of variance. That means that we've got one independent variable and one dependent variable. When you're doing an ANOVA, there's always three things that you want to consider: significance, effect size, and power.
Significance, effect size, and power. And power, and power, and power, and power, and power. Significance, effect size, and power.
So this week we're talking about power, which actually relates to sensitivity. How sensitive is your test in being able to detect that you have a difference if you really have one? In statistics, there's the law of large numbers, which means that the greater your sample size, the more accurate you're likely to be, which relates to the more power you have, or the more sensitive your test is to detecting a difference if you really did have one. This is a conceptual formula. It's not to be used mathematically, meaning you don't actually put your sample size and effect size and within group difference here to find power. This is just something that will help you understand the relationships between each of these ideas. So as power increases, sample size increases, meaning if we don't have enough power in our study, we can always increase the sample size to get more power. At the same time, as effect size increases, power also increases because they're directly related. Within group difference, which remember is our error term, as that gets smaller, our power will also increase. At the same time, if our within group difference increases, our power will decrease. So there's two different ways to calculate power. This is a phi or phi coefficient. You can find it in these big long tables in the back of your book. But this is what the equation looks like. N refers to the number of subjects in each of your groups, which is 4, not 12, which is the total N. This is the effect size that we calculated from last week, which is 0.443. So you just put it into the equation and you get a phi coefficient of 1.78. And this is when you would go to the back of the book and look it up. Look it up to see where in the table it goes to which power line. So the table that you use will depend on your degrees of freedom for your numerator, meaning the number of groups that you have minus 1. In this case, it's 3 minus 1, or 2. And that will determine which table you specifically use. So this will give us a power of around, a phi coefficient of around 1.78. If you look in your table and follow the lines, you'll get a power of just under 0.8, which is usually what we're going for. So this phi is also called the non-centrality parameter. Remember, the number that we get here is not the power. You put this into the table to find the actual power level that you need. Another application of power is to calculate what sample size you need to get a certain desired power level. Usually we go for around 0.8. In this instance, you use effect size again, which is what we calculated last week to be around 0.443, and you use your phi coefficient, which we estimated from the back of the book to be around 1.8. If you put that in the equation, you get around 4.07, which means that we would need around 5 subjects to get a power of 0.8. So these tables are determined based off of your degrees of freedom numerator, which is the number of groups that you have minus 1. In this case, we have 3 groups minus 1, so we're using a degree of freedom numerator, which is 2. According to the non-centrality parameter, or phi, that we calculated to be 1.78, you're going to find that down here. It'll fall somewhere right there. When you move it up, you're going to look for, by conventional standards, where it crosses the 50 power line, which is the 3rd line. Where it crosses that, you're going to move over, and this right here will tell you how much power you have. So our phi of 1.78 crosses the 50 power line around somewhere just underneath 0.8 power. We use the 50 line because it's the accepted standard convention. So in statistics, there's the law of large parameters, which means that law of large numbers.
Yeah.
In statistics, there's the law of large. Damn.
Yeah, me too.
Okay.
Good.